Let's start today's lecture. This is the first lecture of the week number 2. It is 2.1, sorry. So today, the plan for today's lecture is going to be the review of the combinatorics, first of all. And then we're going to discuss a bit about the probability theory. So we're going to define some basics of the probability theory. So have you watched the second lecture of the last week? So where we discuss about the fundamental counting rules. So, and one of the most important one states that if one event can happen in n different ways, and if another one can happen in m different ways, then altogether they can have m times the n different ways, right? So today we're going to do a couple of problems to use this rule. So I would like to start with this rule. So how many different 3-digit numbers exist, or you can create, if you can use only this 5 digits? 1, 2, 3, 4, 5. So what I want is, I just don't want to write down the answer. I just would like to try to understand what is the solution. So what we can do is, we can assign the different numbers here, right? So for example, I can assign 1, 1, 1 for all of the 3 digits, okay? So this is going to be one of the options. So now what I want is, I would like to fix these 2 positions, the first position and the second position, and I can play with the last position, okay? So how many different possible ways I can create for the end, for the last position? 5, right? 1, 2, 3, 4, 5. By the way, you can also talk, your voice is also recorded. So, okay, it's okay. So 5 different options for the last digit, right? So if I just fix, for example, let's look to these last two digits, like the second one and the third one. If I just fix the one here on the second position, there are 5 different options for the third position, right? Now, if I just change this 1 on the second position to the 2, right? So if I change this to the 2, how many different options I'm going to have at the end for the third position? Again, 5, right? So again, 1, 2, 3, 4, 5. So it means that for every position for every digit on the second position, I have 5 digits on the third position, right? So how many digits I can create for these 2 positions, like for the second and for the third? 25, right? Because for 1, I have 5 options. For 2, I have 5 options. For 3, I have 5 options. For 4, I have 5 options. For 5, I have 5 options. So in total, there are 25 options here. So 25 options here. So please note that I didn't change the first position, right? So it was 1, and it is still 1. So for 1, there are 25 options. But now, if I change this 1 on the first position to the 2, it is going to be again 25 new positions or options for the second place and for the third place, right? So I can play with the first with the numbers on the first position. So I can change this to the 2, to the 3, to the 4, to the 5. And for every new digit on the first position, I have 25 different possibilities for the second and third, right? So that is why in total, I'm going to have 125 options, right? So for 1, I have 25. For 2, I have 25. For 3, I have 25. For 4 and for 5, I have 25 options at the second place. So that's why at the end, we are going to have 125 options. So it is really important for us to understand this rule rather than just the formulas, okay? So my way of solution of this kind of problems is always, if I'm given some combinatorial problem, so I imagine what is going to be my output. So in this case, my output should be the number which contains 3 boxes. And I usually count the number of the possibilities for each of the boxes. So here, for the first box, I can put 5 possibilities. For the second and for the third, 5 possibilities. Then I have to multiply. And at some point, I'm going to ask you why we are multiplying this, why we're not adding this. So the multiplication happens because for each of the case here, I have 5 different options here. So that's why we're multiplying this. Okay? Cool. So let's try to solve a couple of problems. So let's try to solve this. So find the number of the possible 10-character passwords under the following restrictions. So all characters must be lowercase letters. So if all of the letters in your password are the lowercase letters, so how many different passwords you can create? So all of them can be A, for example, or one of them can be A and all of the others can be B, and so on. So how many different possibilities you can create? 26 in the power of 10, right? So again, so we are going to create the 10 boxes. So the logic is here like this. So your output should be 10-digit character, right? So 10-digit password, sorry. So that is why we drew 10 boxes. And for each of the box, I'm going to write down the number of the cases which I can assign. So for the first, it's going to be 26. For the second, it's 26. For the third, it's 26, and so on. And at the end, it's also going to be 26. And then I have to multiply them. And the logic of the multiplication is that for every choice of the digit on the first place, you have 26 choices of the digits for the second place, right? And so on. So that's why we're multiplying this. So in general, it is going to be 26 in the power of 10. So 26 in the power of 10. So what if I just change the restriction a little bit and I say that, hey, all of the digits are lowercase letters, but they have to be distinct. They have to be different. So how many different passwords do I can create? 26 factorial, right? Or 16. Okay. So in this case, it is going to be like this. So I cannot use, for example, if I use the A on the first position, I cannot use this anymore, right? If I use the B, for example, I cannot use the B anymore. So again, I'm going to create the boxes, and I'm going to write down the number of the cases I can assign for each of the box. So in the first place, I can assign any letter, right? 26 letters. So if you choose one of the letters, it doesn't matter which letter, you cannot choose this again, right? So that is why on the second place, there is only 25 cases. On the third position, there are only 24 cases, and so on. At the end, it's going to be 17, I think. Let's write this down. 23, 22, 21, 20, 19, 18, and 17. Okay? Then we're going to multiply. So the number of the cases is going to be always one less than before because you've already chosen one of the letters. And actually, it doesn't matter which letter you choose. It is going to be always one choice smaller. Okay? So at the same time, we can write this down, the solution as the 26 factorials divided to the 16 factorials, right? Or 26 factorials divided to the 26 minus 10 factorials, right? So let me write this down. Why the 26 factorials divided to the 16 factorials is exactly the multiplication of the numbers from 17 to the 26. Because 26 factorials is the multiplication of the numbers from 2 until 26, right? So here I can write down the 16 as well. So then, and the 16 factorial is the multiplication of the numbers from 2 to the 16. So we can cancel this, and you're going to have the multiplication from 17 to the 26. Okay? So please note that this is exactly the formula of P 10 out of 26. Okay? So can someone explain me the formula, interpret this formula? What does it mean, this formula? Huh? So it is basically, you have 26 distinct objects now, right? So you have only 26 letters in your box. So what you need to do is, you need to choose 10 of them, right? And then you need to rearrange, okay? And the number of the choosing 10 objects and rearranging them is going to be P1026. But do you remember there was another formula? It was like a C26 and 10. So what is the difference between C26 and 10 and P? What does it mean? Okay, it means that you've got 26 letters. You just need to choose 10 of them, right? You don't rearrange them. It doesn't matter in which order they're coming. While in this P, it depends which letter you're choosing the first and second, okay? Because the order is important. So the word can contain only the uppercase letters, all the A's and all the B's. So it's going to be an easy one. So for example, like 5 of them are A and all the others are B and so on, like this. So can you tell me how many different passwords we can create? 26 to the power of 10. Only A and B. 2 in the power of 10, right? Because for every box, there are 2 options, and there are 10 boxes, so that's why it's going to be 2 in the power of 10. Okay? Is it clear? For example, if you would just have 2 boxes, 2 digits, right? If you would just have 2 digits, then there would be like A, B, 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 right? 4 different passwords could be created for just 2 boxes. And the logic is like a 2 times to the 2, because you've got just 2 boxes, and for each of the box, you can choose 2 different options. Either A, either B. Either A, either B. Okay? So that's why it's going to be the multiplication of the 2 times. But if you have 10 digits, then you have to multiply 2 10 times. So that's why it's going to be 2 in the power of 10. Oh, that's going to make this problem a little bit more interesting. So the word can contain only the uppercase letters A and B, and must contain each of this. Yeah? Yeah, okay. So instead of counting the number of the cases where both of these letters A and B are participating, it is much more easier for us to find the cases when they are not together, right? There are only 2 cases when A and B are not together, are not coming together. So there's this case, and there's another case with all the A's and all the B's, right? There are only 2 cases, okay, where the A and B are not coming together. So the total number of the cases of creating the password is 2 in the power of 10, and we have to just exclude this 2, so minus 2. Okay? And then this is going to be the number of the cases where A and B are coming together. Okay? Because there are no other cases when they are not together. So what about this problem? The word can contain the uppercase letter A and B, and must contain equal number of each of these letters. 4 cases? No. So the word can contain only A and B, and the number of the A's should be equal to the number of the B's. So how many letters they can be? How many A's they can be? 5, right? So what I have to do is now, so this is actually a different problem, right? It is not about like creating the passwords. It is about the rearranging the letters, okay? Because we know that already that we have just 5 A's and 5 B's, and we need to just figure out how to rearrange them, right? Okay, well, if all of them would be different, then the number of the rearrangements would be 10 factorials, right? If all of them would be different. So this 10 factorial case implies already that these 5 A's are different and these 5 B's are different, but actually they are not. So what we need to do is we need to figure out the number of the cases which these 5 A's are giving to us and subtract this or extract this from these 10 factorial cases. Okay? So if these 5 A's would be the same, would be different, then there would be 5 factorial different case out of this, right? And this 5 B's would be the same, then there will be again 5 factorial cases out of them, okay? And now we are going to divide them to the 10 factorials, 5 factorials and 5 factorials to here, okay? And this is going to be the answer. So the question is why we are dividing this 5 factorial in order to extract those 5, so the similar cases. Why we're not subtracting them? Do you understand the question? So there are 10 factorial cases in total. But we know that these 5 are the same. So that's why we calculated how many cases they would give us if they would be different. It is 5 factorial. So now we would like to extract these 5 factorial cases out of 10 factorial. But why we're not subtracting? Why we're dividing? Do you understand the question? Yeah? So the reason why we're dividing is that this 5 A's, if you just subtract, it means that you're subtracting the number of the rearrangements of these 5 A's when they are coming only here in the first 5 places. But obviously they might come in different places, right? So it means like this 5 A's might come here at the end, or they might come in the middle like A, B, A, B, A, B, A, B, right? All of these cases when these A's and B's are mixed, all of those rearrangements of the A's are always going to give you 5 factorial cases. Do you understand this? If this 5 A's would be not here, but here, for example, then it would be again 5 factorial cases. If the 5a's and 5b's would be mixed, then it would be again 5 factorial cases, right? So that is why we're not subtracting, we're dividing this, because this division is going to extract this 5 factorial extra cases from all of the rearrangements of the A and B when they are mixed. Okay? Cool. So this is actually the formula which we've learned when we are going to calculate the number of the rearrangements of the n objects when some of them are similar, right? So this is the number of the rearrangements of the 10 objects when 5 of them are similar and other 5 of them are similar. Okay? So at the same time, if I looked at this formula, I can see that this is the formula of the C, 10, and 5. Right? So is it clear the explanation of the solution of this problem using this formula? Right? So you are creating 10 factorial cases and you're extracting some of them. Okay? But at the same time, it is the same as this formula. Okay? I just would like, so number-wise, so they are going to be the same numbers. Okay? But the formula-wise, they are different. We used to use this formula for one purpose and this formula for another purpose. But it appears in this case, for this problem, both of them are going to be the solution. What I want is, I would like to explain the solution for this problem from the perspective of this formula, not from this. Okay? You need to just understand the question. Just look to this and just understand the question. I'm not asking you the answer right immediately. So this problem can be solved using this formula, and I would like to explain the solution of this problem using this formula, not from this. Okay? Do you remember the meaning of this formula? It was choosing 5 objects out of 10 distinct objects, right? In any order. Right? Okay. Do you understand the question? Yeah? Do you have an answer?
I guess we have to choose 5 places where we can place A out of 10.
Yeah, exactly. So what I want is, I'm going to have 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now I'm going to choose 5 of them, any 5 of them, in any order. For example, I can choose like 2, 1, 4, 3, 5. Okay? So those numbers here, 2, 4, 1, 3, and 5, are going to be the positions where the A's are going to stand. Okay? We have just 5 A's. I'm just going to place them to this position, to the second, to the first, to the fourth, to the third, to the fifth. Okay? So now, so you're just putting these 5 A's to these positions. Does it matter in which order you're choosing these 5 numbers? It doesn't, right? If you choose them like a 1, 2, 3, 4, 5, these 5 A's are always going to stand here as well, right? It doesn't matter in which order these numbers are coming, okay? So now what we are going to do is, instead of finding the number of the rearrangements, what we want is, we would like to figure out the number of the ways we can generate, the number of the sequences we can generate for the positions of the A's. And if you know the positions of the B's, the rest 3 places are going to be filled with the B's already, right? So for example, you can choose other 5 options out of this 10. You can choose, for example, 1, 3, 5, 7, and 9, right? It means that these 5 A's which you have are going to stand in the first position, in the third, in the fifth, in the seventh, and in the ninth. And all of the other positions are going to be filled automatically with the B's, okay? So finding the number of the rearrangements is the same as finding the number of the possible positions for the A's. So it works only for this case, okay? Cool. So that is why, what is the number of the choosing 5 objects out of 10 where order is not important, is C, 5, and 10. Okay, so that is why the solution for this problem is going to be like this. But again, so it is important, it is not really important what is the numbers, what is the answers. It is more important to understand or interpret this formula. So why this formula here is the solution for this problem. Okay, because obviously later on you will see that the problems are going to be a little bit more difficult. Okay, and it is important for us to understand this now. Okay, so let's do some easy problems. So how many different letters can be created by rearranging? How many different words can be created by rearranging the letters of this word? 6 factorials, because all of them are the same, right? So how many different words can be created by rearranging this 6 letters? 6 factorials over 2 factorials over 4 factorials, right? It's going to be 6 factorials over 2 over 4, right? Again, you can explain this in this way, like these 2 letters are the same, and these 4 letters are the same, so we are extracting the number of the rearrangements of those letters. Or you can again create the sequence of the positions for the h's, right? So you have, for example, 6 positions, 1, 2, 3, 4, 5, 6, and you need to choose only 2 numbers. They are going to be the positions where you're going to place the h, okay, this 2h, and all the other places are going to be filled with the t's automatically, okay? Cool. So let's do this problem. A class in probability theory consists of 6 men and 4 women. So an examination is given, and after the students are ranked according to their performance. If you assume that no two students have the same scores, how many different possible ranking lists we can create? So let's say like a 6 men, 4 females. I'm just going to get the exam results, and I'm going to just rank them to one list. And I just like to figure out how many different possible rankings I can create.
What do you mean by ranking?
Ranking, just a ranking. Just put them in a rank.
Is it again the same answer?
Oh, I don't know. If 10 of them are different, then obviously the answer is 10 factorials, right? So you can rearrange this 10 different items in 10 factorial different cases, okay? If you don't understand, you just create a box again, okay? So your answer should be the list, right? 10 boxes which are written on like a vertically, okay? Then for the first option, you can place any out of 10 students, right? So let me write this. So you can create the boxes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For the first place, you can place 10 students. For the second, you can place 9 students, then 8 students, and so on. At the end, 1 student. So the reason why this is 10 factorials is also coming from the fundamental counting rule, okay? Because you can place 10 students to here, but if you choose one of the students to here, it cannot stay on the second place again, right? Then there are 8 options and so on. Okay, so let's change this a little bit differently. So let's say now, I would like to rank male students among themselves and female students among themselves, okay? But let's say this is not a probability exam. This is, let's say, running contest, okay? In the running contest, it is natural to split the males and females, okay? So let's say I'm going to rank males among themselves and females among themselves, and then I'm going to create one list. How many different lists I can create?
2 factorial multiplied by 6 factorial.
Oh, well, it depends, okay. The number of the cases, the number of the ranking lists you can create for 6 males is 6 factorials, right? The number of the cases you can create for the 4 females is 4 factorials, okay? And now we have to multiply this, okay? The reason why we're multiplying is that, so you've got just 6 males, okay? And you fix them, for example, M1, M2, M3, M4, M5, M6. You fix them. For this ranking of the males, you have 4 factorial cases of the rankings of the females, okay? But if you just change something in the rank of the males, for example, M1 is going to be changed with M2, then you're going to have again 4 factorial cases of the rearrangements of the females, okay? So that is why we have to multiply 6 factorials and 4 factorials. And now he's saying that we have to additionally multiply this as a 2. Why we are going to multiply this? So why we would need to multiply this as a 2? Because already it gives us the answer, right? So 6 do you understand what's going on? Okay, 6 factorial cases. So let me write this down. M1, M2, M3, M4, M5, M6. Okay? This is going to be just one ranking of the males. For every this rank, you have 20 24, right? 4 factorial is 24? 24 factorial, 24 cases of the ranking of the females, okay? F1, F2, F3, F4, F2, F1, F3, F4, and so on. Okay? But if you just change one of them, so if you just make this M2, M1, M3, M4, M5, and M6, it is going to be again 24 cases. And this list, this 24 lists are going to be different from this 24 because these two positions are changed. Okay? So that is why we are going to multiply 6 factorials to the 4 factorials. But he claims that we have to additionally multiply this to the 2 or 2 factorials. Why we need to multiply these numbers already, which is the solution, which might be the solution, to the 2 additionally? Because the list might come differently, right? You can list all the males and females, or you can list all the females and the males, okay? You need to look to these objects as the 2 objects, okay? And the number of the rearrangements of these 2 objects is going to be 2 factorials, okay? All of this list is going to be 1 object, and all of this list is going to be second object, and the number of the rearrangements of these 2 objects is going to be 2 factorials. If you would have, for example, the third category, for example, the kids, right? So let's say like you've got 6 males, 4 females, and 3 kids, okay? The number of the lists you can create when they are sorted among themselves, right, is going to be 6 factorials times the 4 factorials times the 3 factorials. We have to multiply this. And additionally, you have to multiply this to the 3 factorials, okay? Do you understand this, where the 3 factorials is coming from? You're combining the males, females, and kids together, okay? Males, females, kids, females, males, kids, or kids, males, females, and so on. Okay, this is where it's coming. Okay, so this is a quick review of the combinatorial analysis and important formulas. And the reason why we need to calculate all of these cases is to validate the probability.